name's Hillman, so I'm a part-time PhD student at the University of Dundee. And just to declare all of my interests, I actually work full-time for Teradata. If you've ever heard of Teradata, I'm sure the Otto and Bouygues guys have. And as part of that job, I spend a lot of time traveling and a lot of time in hotels on my own and things like that. So about 3.5, 4 years ago, I decided that to fill that time, I would do a part-time PhD, which seemed like a good idea at the time. And my supervisor said to me, getting a PhD is actually not really anything to do with intelligence. It's all about stubbornness. And 4 years later, I know exactly what he was talking about. So I'm just going to introduce a little bit about what the research is, talk about what I've done so far with MapReduce, and then the rest of the talk will be about what we've done with Flink. So the subject is proteomics. Now, I think most people have heard of the Human Genome Project, yeah? So mapping all the genes in the human body and working out what they do. The proteomics is the study of the proteins that are created by the genes, and it's a much bigger problem space than the genome is. And why that's important is it's basically the genome can kind of find out why you get a disease, the cause of it, and the proteome is much more around finding a cure for a disease. So a lot of the work is in finding cancer treatments and new drugs for that they do. So what these guys do is they get a cell or some tissue and they treat it with a drug, and then they run it through a thing called a mass spectrometer, which produces the data that they need for their experiment. Now, these things run for about 2 hours. It's like a big microwave, and you put the thing in it, and 2 hours later it goes ping, and then this file comes out the other end, which is about 7 gig of XML. And I've learned to detest XML over the last 4 years, and anything that's ever done with it. It's a terrible format for that kind of data, but hey, that wasn't my problem, my decision. And these things have got these scans as they scan the cells, and in each scan there's lots of data points. So you get about 80 million data points in one experiment, and it needs a lot of pre-processing. You get this kind of waveform come out, and you have to pick the peaks, because the peaks are the mass of the molecule you've detected. And not only do you have to do them across scans, you actually have to pick them across time as well. So it's like a two-stage process. It's quite complicated, and the processing at the moment is done on a PC-based system, and it can take about 24 hours. So I came along and said, hey, this Hadoop stuff looks good. This is way back in like the mist of time of 2011. I'll rewrite the algorithm in parallel, and then we'll run it in real time on the cluster. And that was the idea. Since then, the lab's gone from 1 machine to 12 machines, so they were sort of stretching off into the distance. So now we're getting, I don't know, 3 or 4 billion data points a day in XML. And it all needs to be processed in this way. So, whatever your definition is, to me that counts as big data in that kind of format, in that kind of volume. And what I decided to do was look at different ways of processing this. We're looking at different formats to store the data in, so HDFS, HBase, Cassandra. The only reason I was looking at Cassandra is because my PhD supervisor is a massive Cassandra fan, so anybody who does anything with him has to use Cassandra. And then we're looking at different ways of processing the data as well, so looking at MapReduce, Storm, Spark, recently Flink. So Flink's only just come up. I've only been aware of it for about the last 3 or 4 months. One of the problems of doing any of this sort of research over such a long period of time is that it keeps changing. So in 6 years, the stuff you're using at the end wasn't even there when you started. So you have to keep kind of evolving with it. But It's been going well so far, and because, you know, I always say, I've been working in computing for a long time, been working in IT, and it kind of, if somebody asks for something and you build it and it works and nobody complains, that's what they get. And then if somebody else asks for something similar, they get that as well. So the problem with doing a research project is I suddenly had to get into the point of proving that this was the right way to do it, rather than just doing it and it working. So these things hardly ever seem to get mentioned, you know, when we're talking about distributed computing. But these well-known laws about parallel computing seem to be really relevant to this. So there's a thing called Amdal's law, which kind of says that in any parallel process, there's always one part of it, or some parts of it, that cannot be parallelized. And whatever speed up you've got is always limited by that parallel part. So you don't get true linear scalability. And then there's a guy called Gustafsson, who then said, well, actually, it doesn't really matter what you speed up, because the more you speed it up, the more data you'll get to put in it. So the size of the problem is never fixed, which is a bit like why it doesn't matter how much you earn, you're always overdrawn, because, you know, you can just spend it whatever you get. And that's definitely been true in this project. So, you know, starting with one mass spec and ending up with 12. And then there's Gunter, who came along with, actually, as you get more and more parallel, you get worse performance, because certain things, certain communications, sometimes, you know, with us, with the scans, if you've got 40,000 scans, if you imagine using 50,000 nodes, you're not going to get better performance, you're going to get worse, because you're going to have to split scans rather than processing them. So yeah, just things to bear in mind on that. So what have I been doing? The first thing I did was build a Hadoop cluster, which was there. That was using PCs that I took out of a skip out of the office. And that was good fun. And the problem with like building this kind of stuff yourself is that personally for me, I had to learn more about networking than I ever wanted to know, and more about the insides of Linux, but it's still useful operation. But since then, the thing's just, you know, it's too noisy, it's too slow. I used to, you know, if I could go in and dial in, I'd start the thing up remotely on the network cards, and I could start this thing running. And at least, you know, 5 to 10 minutes later, my phone would start ringing. It would be the wife going, "What are you doing?" Because it sounds like an aircraft taking off in the room. But so since then, I've gone for a sort of big gaming PC type idea. I got 8-core CPU, 6 SSD drives in it, and each SSD running a VM, so I can do a kind of virtual cluster thing. And that has been perfect for all the testing I've needed, because it's like my own little version of EC2, you know, I can kind of fire up different clusters and slow them down and test stuff. So that's been really good stuff. So to look at what we've been doing, the data comes, as I say, in these scans. So imagine that across there is actually a snapshot in time, and this scale is weight. It's the molecular weight. So we're trying to pick the tops of these peaks. Okay, which is a fairly simple operation in essence, but it's actually, the maths of it get really complicated because the peaks overlap and you have to measure the area under the curve and all this kind of stuff. And then once you've got those, you have to do this thing here, which is called de-isotoping. So because of you've got carbon 12, 14, 16, 18, you get different weights which are actually the same thing. So these have to be picked as well. Which actually, this is like I always call it, Chris's first law of computer science, which is no matter what domain you work in, you have to learn every single term, acronym, jargon that they use, and in return, they'll learn nothing about what you use. So in the morning, you know, they'll say, "Oh, did you get the missed cleavage on the tricid molecule?" I was like, "What are you talking about?" But then if I said, "Oh no, it ran out of disk space," you'll get, "Oh, don't give me all that techie rubbish." And he said, "Come on. Disk space." It's like, but anyway, so this process here actually fits really well into a map task. If you're trying to think of it in a MapReduce idea, each scan is completely independently processed of the others, so it can be completely parallelized at the scan level. And back to that Amdau's law, that is the smallest unit of parallelism we can create on this, so that has a fixed cost that you can't get any faster than. The next step is to line up all of those peaks across time. So the scans are going this way, and then across time you get these molecules which look like that. And that kind of mountain in the peak gives you the actual amount of the molecule that was there. So this kind of, to me, was, hey, that's a reduced task. You've mapped it across, you've picked the peaks, and then you're kind of aggregating them down. Great. That worked really well. It kind of fitted what I wanted to do, so off we went. But then the problems you get are that XML is a rubbish format for parallel processing. If you put that onto a cluster, the most likely thing is you're going to split the file in between tags, and you have to read the thing sequentially. So what I came up with was pretty much any data that's put on a cluster, you have to get it on the cluster in the first place. You've got to get it from where it was created onto the cluster. So the idea was, if you wrote a new copy, a file copy function, that actually picked out the bits. This here is base 64 format data that we actually want. Pick the bits you want, and then you can actually have a nice format arrive on your cluster from the XML. So create a file format that is perfect for parallel processing, rather than try and fiddle around with it as it's on the cluster. So this is working for HDFS, Cassandra, and HBase. Works really well. And then we can run the MapReduce code on it without worrying. The other issue was when we went into looking at the reduce code to pick these 3D peaks, you had to kind of work out how you're going to partition it. How are you going to, because we don't want one reducer. So I decided to do it by molecular weight, which is across here. And the issue with that is that some of these peaks cross the boundary where you've split it. Now we know from the biology what this theoretically can be, what the width of a peak could be. So we came up with the idea of having an overlap between the reducers. So this bit gets some of that data and this gets some of that data, so you get an overlap. So you're guaranteed to pick it, but then of course you end up probably having to duplicate somewhere in case you picked it all. But yeah, that kind of worked. The answer's right, which is the most important thing when you get the data. The other issue was skew. So in any parallel system, skew is always the killer. So this is the molecular weight, and because this was human proteins, they all cluster around a certain value. Different biologies, different animals have different clusters, but anyway, so I had to come up with quite a complicated custom partitioner to try and ensure that each of the nodes got a fair amount of data to work with. Yeah, it was a right pain actually doing that. And I kind of came up with, if you're gonna experiment with parallel processing, one thing is don't spend too much time coding on a pseudo cluster with one node, because you don't know this is going on with one node. You need at least two nodes to work out that there's skew there. And the other thing is don't spend too much time testing on a small data set, because one of the things I ended up with that I had completely missed was a horrible nested loop, which gave me like this ON squared execution problem. So when I was running on the small data set, you never noticed it. As soon as I put it on the full data set, the thing never finished, and I had to go back and change all that code 6 months after I'd written it. But anyway, the results are good. This one at the top here is current software that does this on a PC, single-threaded. This was my results, and they matched. And I was actually on a flight back from Istanbul when I was doing this, and I was giving it, yeah, like that. And there's like the woman sitting next to me was like trying to get away, but it's like, yeah, it actually works. So. Just to recap that, so we've got the map step, which picks the peaks. You've got this shuffling, which reorganizes it and gets it all back on the right place, and then the reduce, which is done in these mass windows going down this way. And yeah, it works. We kind of know how many scans a second we can process, how long these things take. So you think by scaling a cluster, you can get this quicker and quicker. The XML transforms work. You can read and write from HD. I can't write back to Cassandra for some reason. They keep changing that interface like every 3 or 4 weeks, I think. But anyway, so it kind of shows you could speed this up by using this, but the actual speed is actually a bit disappointing, really, because on my PC, if I just run the current process, just on this pre-processing part, there's another part which takes a bit longer, but I can run it in about 35 minutes, just this pre-processing on the test file. The MapReduce task takes about 28 minutes, 4-way parallel. So it's not that impressive, but given that the Hadoop process is actually running in VMs against the bare metal, there is a lot of latency there. But still, it was far from real time, which is what we were aiming for. So I guess must have been back in July. I was doing some work reviewing proposals. And I kept reading about Flink, and Flink kept coming up, and they're talking about streaming and dataset API in the same place. I thought, I was actually looking at Spark at the time, so I thought, I'll switch and have a look at Flink. And so far, Flink has got to be the easiest thing in the world to install. It's just ridiculously easy. It's easy to understand. The documentation on the site is great, and the best thing for me was adapting the current code that I had was so simple. It just was, it was like a couple of, an hour of reading it and two minutes doing it. So yeah, I really like it. So looking at how the differences work out. Actually, I wish I'd listened to Stefan's talk yesterday and the guy from Google this morning. Yeah, if I'd listened to them about a year ago, it would have saved me a lot of work because I just gone straight to doing this. But so this is a standard MapReduce job. Yeah, this is how you sort of orchestrate what's happening on Hadoop. So you say wherever it is, which map class you've got, which reduce class you've got. You have to say how many reducers you're going to use. So in this case, I've split that file 104 ways in the reduce step. So there's the MapReduce there. Input-output formats. It's just a kind of boilerplate thing. But hey, it works all right. And then reading the data in, it's always annoyed me with MapReduce, this key value pair thing, that when you've got quite a complicated input format, you have to read it in as like a key and then this string that then you have to use string split to split up to turn it into the objects you want. So that's the mapper. That's reading in the data from HDFS. This is reading in from Cassandra, which again is fairly simple. There it's a bit more, you can read direct from the table, obviously. It's not a concatenated string. And then on the mapper, you then have to write the data back to the file system where it's shuffled, which is this bit. So I've now got to concatenate all those things back together again to write them back out. And then my reducer reads them in and then does the string split again to split it back up. So I've read it in, written it back out, read it in. So that's the way the Hadoop process works. Now, when we switch to Flink, basically could take, there's an example on the website of the Hadoop, using your Hadoop input and output format. And I could basically just take that example and stick my map class into it, and it worked. Just worked straight away. I didn't have to change anything in it. Because you're setting up the Hadoop input, you read in the it's tuple, by the way. Everyone says tuple. It's not, it's tuple. It's like tulip and tuborg. So yeah, right, so there's my map function. There you go, map HDFS, and it works. And it's fast. It's faster than the Hadoop side by about 3 times without changing anything, which is great. I like that because it made me look good and I didn't have to do anything. And then I stuck the reducer in, And again, that was really fast. And I was thinking, hey, this is because you're not writing the data out, reading it in, it's all doing it here. But actually, it's because the results came out wrong. So it was really fast, but wrong. And the problem is, it was ignoring my custom partitioner. So where I'd done all this work to move the data around and sort it in the right order, this wasn't having any of that. It wasn't quite the happy ending I was after, because I then had to go and change some code to get this thing working. But on the map side, perfect. So I'll come back to that about the reducer in a bit. So, okay, so yeah, and then I'm writing back out to HDFS here, yeah, emitting the output. So the results so far. It's good. Again, this is on a test set of code on my PC at home. But the Hadoop mapper was 12 minutes. The Flink was 4 minutes 50. The Hadoop mapper and reducer together here was 28 minutes. Flink. This is with it giving the right answer, by the way. This is with it fixed. 10 minutes 20, and the existing code was 35. So I was really pleased with that. It was like, this is great stuff. It's easy to install. It's easy to change the code. I didn't have to mess around with what I'd already written. Was like, it was like at least half the speed, if not three times faster. But it's still not real time. Yeah, it's still not what the aim of the thing was for. As I said, we know if we can process so many scans a second, if you can make the cluster big enough, maybe it'll work. So I started looking at it and thinking that the mass spec actually takes 150 minutes, depending on what settings they're using. But it takes like a couple of hours to run. And all that time, the data's being written to disk. So actually, if we could stream that off the machine rather than write it to disk, then by the time the thing finishes, we've almost finished the processing, yeah, because we can do the mapper, and then it's like, oh, this is confusing now because the reducer is then looking at all the data. So how are we going to fix that? So there was quite a nice little trick again that I hadn't realised you could do in this. And again, if I'd have listened to the talk we had yesterday, it would have saved me a hell of a lot of time. So the idea is I'm now using Kafka on the output file to kind of simulate the stream, so pretend that it's streaming, because to actually make it happen would mean Thermo, the equipment manufacturer, doing all the work. So I guess, hopefully, if this works and we get the right answer, it might be something to be able to show them that they can do it. So Kafka streaming the file, and then using the Flink streaming API to process it as it comes in. So again, the map process was really easy to bring into that streaming process, because you just bring in one scan at a time, and it basically works as a map. That's it. And it was funny. One of the guys said that like streaming is a superset of batch, and I'd always thought it was the other way around. But when you actually start using it, you realise that it is. That it's actually more. It does the stuff that batch does and more. So yeah, the mapper was easy. The reducer, I had to go back and spend some time with the life sciences guys to understand the way these things work. And they came up with this word, Aleut. I think if you asked 95% of native English speakers, they wouldn't know what Aleut means. But it basically means that I don't even know. No, it means that the cell, or whatever it is, the mass of the thing that's being emitted, it comes out in different scans over time. So it doesn't all come out at the same time of the machine. It elutes over a period of time. And the maximum time that could happen over is 10 seconds, apparently. And I didn't know that before I started doing this. So whereas I was processing the whole of that reducer over time, you could actually do it in 10-second windows. But of course, we don't know which scans those 10 seconds are in. So we have to use the overlapping window method. So you process it here, process it again until you get the whole of the curve. Because we do know from the maths whether we've got the whole thing or not. So we don't get the duplicate problem, because if we've only got a partial curve, we can just discard it. So it looks like that. So yeah, we process scan 1 to 10. It's actually, you get 4 scans a second, but so it's one scan 1 to 40, and then we process it again and again and again and again. And what that means is when the machine goes ping and it's finished, that I've only got to wait 10 seconds for that last 10-second thing to run, and then I've got it. Yeah. And this was like, why didn't I think of this before? Because you could do that with MapReduce, the same. But then I think, of course, the problem is that I'm processing all the data 10 times, which would be crazy if you were doing it in a batch. But because I've got all this time I can wait because the machine's got to finish, it doesn't matter anymore. So I can actually get this thing. And I thought, 10 seconds, that's good enough for the near real time for me anyway. So the other really nice thing about this was it kind of took away all the complications that I'd artificially induced by making it a MapReduce problem, because I processed this way and then processed that way, thinking that's the way you did the aggregation. And that was the way MapReduce was making me think. So this problem with the overlapping windows and the distribution on the cluster, that wasn't really a problem. It was I made that the problem. Whereas when we go to the overlapping windows, all of that problem with distribution goes away now, because you get 10 scans per node, and they're going to have a regular amount of data. They may not have a regular amount of data processing. You tend to find the scans in the middle of the run have more products in more molecules in them, the top ones, but that's for another time. But yeah, and there's no need to overlap and deduplicate, because we just get the data out as it wants. I was going to show you, probably had enough of PowerPoint. Let's have a look, see how it's running. So that's the file format. You've got all this horrible base64 encoded data, which has got the float arrays in it. This is the time here. It's annoyingly in decimal minutes, which is a ridiculous way to store time. So what I did was set up, this is my data streaming job. So I'm reading from a Kafka stream here. There is scheme screen. That's the topic of the Kafka thing. Using this Kafka consumer, I had real trouble when I started doing this, because I couldn't get that. The jar didn't contain that, and I fiddled around, and then eventually I read the documentation properly. And it said to add, quite clearly said, add this dependency in the POM, and then it worked. So yeah, RTFM was the answer to that one. So now when I get the Kafka streaming, I can then, this new stream map is basically exactly my map function from Hadoop. It's just I've deleted the interfaces. I've replaced the read from HDFS with a tuple 2, and the same on the way out. So when it runs, I'll show you here. This is just Kafka with a console consumer, so you can see it running. And here's me streaming the file through Kafka. So the bottom window is running the stream, and you can just see there all of that base64 data arriving in the stream. And then when I run this, please work. There you go. That's my actual weights of the molecules, peptides as they're called. That's the actual molecules that have been detected in the stream. That's great. It's so much simpler than it was before. And the answers are still right. So I haven't actually got round to benchmarking all this yet. It's like the next thing that I need to get done. Let me get that PowerPoint back on. Just to show I wasn't doing anything corporate with Teradata, I made the slides myself, and I did them as amateur as possible. I did that on purpose. It's not that I'm rubbish with PowerPoint. So, but I mean, one of the best things about this is it now means we can get this kind of information factory in the lab. So all of the kind of problems they had before where the files were on the machines, and then somebody had to copy them onto the processing machines, and then somebody had to take them from there and give them to the life sciences guys, and then their results went somewhere else. A lot of that has kind of disappeared because the machine, you know, this is with the proviso that we can get Thermo to stream the data, but the data will just stream through the processing system and land into a database somewhere that they can access the results straight at. So a lot of that kind of ETL process has gone, and a lot of the data management, which is very nice. So what I've got left, I need to get the complete stable working system. Yeah, I need to go back and finish the work I was doing with Spark so that I can compare them. I half a mind whether to drop Storm now and just not bother with it. But again, I think the spout and bolt thing kind of works well with the way I've got the problem split up. There's some previous research been done on the second part of the problem, which is the longer part, which is the database lookup. So I need to make sure I can feed the data into that. And then, yeah, pay for some EC2 time and the small matter of actually writing a thesis, which is the fun bit. So, yeah, I love that quote. My area of study has become so complex I can no longer just Wikipedia the answer. So, but now I know I can ring up the data artisans guys. So. Any questions?
So, Spark, you haven't been starting experiments with Spark?
Yeah, I'd started to do the streaming code in Spark, not the streaming code, the rewriting the MapReduce job in Spark, but I'd never got it finished. Because
how you plan? You plan to use Spark streaming or Spark in general, just batch?
Just batch, yeah.
Just batch.
Yeah, it was only when I started looking at the Flink streaming architecture that I switched to streaming.
Because streaming like this, as you said, it gave you like near real-time results, huh?
Yeah,
right? Because so why are you then trying to do the Spark if you're going to do it in batch? I mean,
well, yeah, I started doing it. Now, when I go back to it, I'll do Spark streaming. I won't bother with the batch side.
Because it's interesting for the community to compare the two systems.
I want to be able to compare Spark and Flink.
Yeah, that would be great, huh?
Yeah.
Very good.
Okay.
So when you were talking about pretty much the right skew distribution when your first version of MapReduce, and you're saying it's sort of a pain in your ass because you have to sort of find a clever way to, I'm going to assume, partition the mass equally across the nodes? Is that what the big issue was? Yeah.
It was to get the data spread evenly across the nodes, but not just, it was also the processing, because the denser the data was in those areas, the more of these peptides there were. So you could send a whole load of data to one node, and it would just run through it and go, there's nothing there. So yeah, it was. Yeah.
Right on. But does that mean at the end of the day, something as naive as perhaps log transforming the distribution to get it somewhat bell-like, and then taking quantiles, or rather doing a quantile partition on that log map, and then inverse logging it?
Yeah.
Would that have given you sort of something that would have been like sort of equi-massive?
Yeah. So I did try a couple of hashing techniques. Didn't actually get too complicated into it like that, because it was basically this idea that it wasn't just the amount of data that was the problem, it was the amount of signal in the noise in that data that was causing me the problem. Yeah, and it was pain in the arse is exactly the right phrase.
Right on. Thank you for the presentation, by the way.
Yeah, I was wondering why you're trying to put Spark and contrast, and have you also looked at Dremel, so Apache Drill, for example, because you have tabular data that you want to process? Yeah, no. The reasons I chose the systems I chose at the beginning was actually the four different ways of storing the data. So distributed file.
columnar, which was HBase, NoSQL for Cassandra, and then something called Aster that I haven't talked about because it's a Teradata product, so I didn't want to talk about that, which is a relational database. So they were the 4 storage, and then processing was originally going to be MapReduce, Storm, and Spark. But yeah, I've tried to keep up. But yeah, I hadn't looked at Dremel or any of these things. So yeah, 6 years isn't long enough to.
Okay, hello Chris, and thank you for the great presentation. Just one thing. In your opinion, I mean, please correct me if I'm wrong, but as far as we understood, what you do is take the results from an experiment of one machine, which produces a sequence of data, and then pre-process/process the data according to a certain schema which you introduced. Do you think it would be possible to apply this to multiple results from multiple machines? More to the point, take various data sets and then use them to query and obtain some results?
Yeah. So yeah, I'm not quite sure I understand. So the idea is to have a central cluster, and all the machines just throw their data at it, and it write the results out to some kind of data store somewhere. Do you mean querying it while it's streaming? Is that, do you mean? Or?
Yeah, what we do is actually take data sets, already generated data sets, and using batch processes, query them in order to obtain results.
Yeah.
But I'm thinking, as you said, maybe we can do something like this and query them as they're streaming out.
Yeah.
I'm thinking about genome sequences right now.
Oh, okay, yeah. So one of the problems with the proteomics side is that they're actually trying to measure proteins, but because proteins are too big for the machine, they have to cut them up into small pieces called peptides. And if you queried the results of the 10-second windows, you'd get the peptide, but you wouldn't get the complete protein. So as far as I understand it, they need to get the complete result set before they know what proteins are in it. But if that wasn't the case, they do this thing called replicates. So you run the same experiment 5 times just to check there was nothing screwy in it. So if you were doing QC, you could probably do QC in real time there, couldn't you? You could join 2 results, yeah. That'd be good, yeah.
And thanks for your talk.
Okay. Cheers.